Hello everyone, my name is Michael Jacobson and I am accompanied by Tin-Chun Wen and Xin-Wen Zhao. Our research is going to entail the personalization of stiffness for an ankle foot prosthesis emulator using human-in-the-loop optimization. We are a part of the Rehabilitation Robotics Lab at the University of Illinois at Chicago. For our overview, I will go through an introduction, methods, results and discussion, and conclusion. Before I do that, I'm going to play a video that will visually describe our research and our experimental protocol. As you can see, this is our mechanism that we utilize. I will go into more depth on the following slides. This is also our overall setup for the system. As you can see, we utilize a simulated amputee for our experiments. We optimize the parameters of the ankle foot prostheses using human-in-the-loop optimization. We use Bayesian optimization to select the stiffness parameter and set it to the AFP controller. Human-in-the-loop optimization selected various stiffness parameters, and the best stiffness reduced the metabolic cost by 5% compared to the control off. Okay, moving on. The issue that we are addressing that individuals with a below knee amputation present a higher metabolic cost. In previous studies, metabolic cost of walking was reduced by adjusting mechanical stiffness. And what we explored was the importance of this personalized stiffness parameter using an ankle foot prosthesis, specifically a robotic ankle foot prosthesis that actuated in 2 degrees of freedom. As you can see on the right, depicted as a CAD model with detailed description of our ankle foot prosthesis. The mechanism is a 2 degrees of freedom ankle foot prosthesis that we approved upon. The improved assembly allows for reduced maintenance during walking trials, and this reduced maintenance was enacted by a new strain relief assembly. The strain relief assembly entailed 2 parts, a FDM printed polymer and a TPU printed polymer. The use of these 3D printed polymers reduced device weight by 0.1 kg. It's also notable to mention that for our experiment trials, we restricted the degree of freedom to 1 degree of freedom. This 1 degree of freedom was actuated by the 2 toes, which are the orange components in our figure. They were pulled by the boating cables and it generated a plantar flexion. And now Tin-Chun will review our controller setup.
Okay. Hi, my name is Tin-Chun. I'm gonna talk about our controller. Our controller was composed of 3 layers: low-level, mid-level, and high-level controller. In low-level controller, it controlled ankle position, ankle torque, motor position, and motor velocity. The mid-level controller was a walking controller, which divided gait into swing phase and stand phase. We further divided the stand phase into pentaflexion and dorsiflexion. So we have 3 different walking states, which was decided by the torque and ankle value. In the mid-level controller, we generated the ankle torque curve, which shows in the figure on the right. We use this curve to get the desired ankle and torque. You can see that in different stiffness parameter, we will get a different ankle torque curve. So we use the high-level controller to find the best stiffness parameter by using Bayesian optimization based on the metabolic cost. Okay, next. Okay, this is our overall setting of the experiment. In figure A, the mid-level controller generated the angle torque curve. It decided the desired angle or torque and then sent it to the low-level controller. And in figure B, the low-level controller received the desired signal and conducted the position or torque control. While the subject was walking, we got the breathing and heart rate from the device, and we calculated the metabolic cost in figure C. Then we send the metabolic cost to our high-level controller to do the patient optimization in figure D. The next stiffness parameter was calculated in here, and it will be used by A to generate the angle torque curve. The patient optimization is a method that using previous data to predict the value of the best condition. During the optimization, it has 4 points randomly in 4 different ranges. Like our range of stiffness parameter was 0.5 to 1.5. So it tested 1 point in 0.5 to 0.75 and another 1 point in 0.75 to 1 and so on. And after that, it tested the point which had the highest expected improvement. Then after some point, the curve will be converged and we got the best and the worst conditions. Okay, next. For our experiment protocol, we follow the table on the right with walking speed 0.9 meters per second, which is a self-selected comfortable speed. We conducted the pilot study with 2 individuals with simulated amputation. And we let subject stand for 3 minutes in the beginning and then work for 5 minutes with control of mode, which was just holding the motor. After that, we conducted the optimization for 12 minutes to get the best and the worst condition. Then we did the worst and the best condition again. We conduct the control of mode 2 times because we wanted to make sure the metabolic cost was not influenced by tiring and adapting. The subjects had some break time same with their working time for recovery of breathing and heart rate. For example, they had 5 minutes break time after the best condition and 12 minutes break time after the patient optimization. Okay, and then Xinyuan will talk about our result.
Hi everyone, I'm Xinyuan, and now I will discuss our results. And you can see on the right side, the figure is the angle torque mechanism for the best condition, and those data are from 2 subjects. And in the figure, we show the desired torque, which is the blue light, the mean values, which is the black light, and the standard deviation, the gray areas. And we have present 4 curves on the figure. The first curve is angle torque curve, and then the ankle position, and ankle torque checking performance, and finally the ankle power. So from the data, we can set the ankle foot prosthesis emulator present a wide range of torque with a small checking error, which is less than 1% compared to the peak torque for all conditions. For the errors, we use the RMS, which means the root mean square errors between desired torque and actual torque. And the emulator also showed a wide range of motions in ankle angles and can provide a high powers up to 1 kilowatt. Okay, next. And you can see the tables. We use the Bayesian optimization to select the best and the worst stiffness parameters. And for the subject 1, the best stiffness value is 1.5, and the worst is 0.5. And for subject 2, the best stiffness parameter is 1.15 and the worst is 0.5. And you can see on the right side figure, the left one is the experiment setup, and the right one is the metabolic cost reduction for the subject 1, which is we use the blue bar, and subject 2, the orange bar. The best stiffness for the best condition, the subjects 1 and subject 2 can reduce their cost of walking by 5% and 6% on average compared to the control of condition. And the worst parameters for the subject 1 and subject 2, they increase the metabolic cost by 3% and 1% respectively. Okay, next. And you can see on the right side figure, this is the metabolic cost landscape of subject 1 and 2. The blue lines are the mean metabolic cost curve, and the gray area indicated the uncertain of the curve, and the red star indicated the collected data. So in conclusions, we conduct a pilot study to test the importance of personalized assistance in ankle foot prosthesis with individuals with simulated amputation. We also improved the robustness of our previous ankle foot prosthesis emulators and employee human interrobation optimization to personalize ankle foot prosthesis parameters. And the pilot study showed that the optimization really helped to identify the optimal stiffness parameter set, which can really reduce the cost of walking. Okay. And this is our whole presentation. Thank you
Thank
for
you
your time.